that the neighboring cells use different frequencies in order to mitigate possible interference. So those are basically the two generally contradicting terms, and it's a challenge of finding trade-off between them. So of course, on one side, you want to have as little interference as possible, right? But then on the other side, you want to serve as many users as possible. And if the frequencies or the bandwidth that you are allocated with is limited, well, those two are kind of contradicting terms, right? Other thing which is commonly done is that you can get the initial approximation of frequency planning by using hexagons, which more or less corresponds to the contour of equal power from your base station. And then we talk a little bit about clusters. So of course, here you can see just a pre-example of one cell cluster, four cell cluster, and the 7-cell cluster. And again, going back to what I said earlier, right? The larger clusters, larger cluster numbers within the same bandwidth, with the same frequency allocated, larger clusters prevent interference, right? But it also reduces the amount of users that you can serve, simply because the same resources are used to cover larger area. And then also we talk about the process of handover. So obviously, if we have multiple cells, this is again the aspect of the mobile network as a network, as a system. And typically, of course, you would like to do seamless transfer of the link between different base stations, and you don't want actually user even to notice that they are moving from one base station to another. And we talk about the broadcast control channel, which in a relatively efficient way allows you to transfer the calls, by monitoring power of control channels of different base stations. Lastly, we talk about the multiple access technique. So just going back to something which we discussed in lecture number 1 or lecture number 2, but this is actually really, really important. And hopefully now you could see practical aspects of multiple access techniques. So in the case of the GSM, which is the oldest or one of the oldest standards for mobile communication, the very basic one, and it uses actually a combination of FDMA, so frequency division multiple access, with TDMA, so time division multiple access. And basically by combining that, so each frequency channel would have 8 different time slots, right, divided between different users. So basically the TDMA multiplies by 8 the factor of the user that could have been served with the frequency by using only the FDMA channel. Okay, so that's more or less the benefits of that. So are there any questions so far of what we discussed in the past? All right. So now we move on to well, half a generation upwards, so to say. So as I mentioned, GSM was the oldest standard for mobile communication, and after that it came the UMTS, which stands for Universal Mobile Telecommunication System. And important concept that this actually introduced, which of course were adopted also in the subsequent generations. So it's not that I'm talking about UMTS, the historical evolution. It's just a way of when it was introduced. So with the UMTS, the idea was to have like a universal protocols for data communication. So, well, GSM, it's a very basic standard. It was optimized mainly for voice with, a little bit of internet connectivity, a little bit of text messaging. But, soon people realized actually that the mobile communication is much more than just voice, than calls, which I believe we see how it evolved nowadays quite clearly. And so with the UMTS standard, it was supposed to embed more data communication and data transmission rather than this focus on voice-only techniques. And as part of that, it also two kind of new concepts that it introduced. So one was support for different size of the cells, but not only in the sense of size of the cell, but also accepting that different size of the cells can differ functionally. So what we mean by that? So typically we have a division here between picocell, microcell, macrocell, and hypercell, right? So each of those will comprise different area. So typically picocell, that was back then a new concept. It supports coverage of up to 100 meters. So that was something that you could have, for example, in a building. This idea is actually very often implemented on the stadiums and events. So many stadiums right now, they would have a dedicated picocell or sometimes a nanocell base station, which cover just the area of the stadium, right? So basically, in the context of soccer games, any sporting events, any concerts, you have a lot of people, gather at some small area, relatively small area. Most of them, would like to, make some picture, make a movie, and stream that or send to their friends who are not on the stadium or on the concert, right? So that amounts to a quite heavy amount of traffic. And basically, if you would rely only on existing microcell or macrocell infrastructure, well, you'd end up bottleneck, and that's exactly what happened in the early days, right? That simply the certain base station in proximity to stadiums were kind of blocked or jammed, simply because they were not capable of handling such amount of traffic. And of course, on the other hand, sporting events are like a one-off opportunity, right? So obviously the mobile provider were not very happy in investing money to improve the capacity of the base station, right? If it's used for 19 minutes over 1 week time, right? That's very that's just like not making their business case go forward. So at that moment, there's a picocells pretty much solve that problem, right? So you can have define a dedicated picocell with separated antenna base station, which is around the stadium or even some sectors of the stadium. And then you can just turn it on whenever the game is on, and yeah, that's that. So in principle, different size of the cell, they have a different coverage. So 100 meters, that's typically considered for the picocell. Microcell is up to 1 kilometer. So this is the most common in urbanized areas. So I would say nowadays, actually, in big cities, well, in Wrocław, you would even probably have cells smaller than that. So up to like few hundred meters. And then there are like the big macro cells, which are on top of building towers, masts, etc., etc. Okay. What is also interesting here that those cells are kind of mapped with different propagation channels. So that goes back to the lecture that we had earlier on. So typically for the indoor communication, this is like the very short range communication with relatively low delays, and that can also see very high speed transmission. So I mean, up to 2 megabytes per second. Of course, those are the numbers are in the time when the standard was defined. But the general message here is that for picocells, defining like a very small cell allows you to significantly increase the communication throughput. So up to up to 4 times. Also, in terms of the picocell, you are not really expecting high speed of the movement, right? So, for example, in terms of the Doppler effect within channel propagation, your channel is much more stationary than with other types. So basically, typically the base station tolerates speeds up to 10 kilometers per hour, or even lower. Basically all the speeds that originate from human movement. So obviously, if your picocell is 100 meters, there's no point of considering somebody that moves 100 kilometers per hour through it. That's just going to be a very, very small fraction, right? And then when we move upwards in size, we can also see that the transmission speed deteriorates. All right, so we got for microcell, we got 1/4 of this of the speed that we had with the picocell. Then, of course, we need to account for much more complex propagation, much more complex. Basically, because of the larger area, the delays will be different, and the time response of the channel will be longer, or more spread in time. And also, the channel itself will be more dynamic because, according to the standards, it is expected to support up to 120 kilometers per hour, which is, for instance, what you would experience if you're driving a car on a motorway or on a bypass. That's not uncommon speeds, right? And well, if your car or you're talking, you're using any data, right? So even maps or traffic information through your mobile phone, that's basically the speeds where you still need quite a good connectivity, right? So 120 k's, it's kilometer per hour. It's not something extraordinary, really, if you consider the Doppler shift. Then we have the macro cells. Again, the speed, acceptable speed of the base station, it's further increased. The required transmission. Sorry. Actually, just now noticed this is in Polish. Sorry about that. So basically, this column states the speed of the mobile station, whereas the last one is the speed of the transmission of the link. Right, and then of course we get something like a hypercell, which is basically a satellite base. So that's really, we're talking about a few hundred kilometers. This would be typically the case with remote areas. All right. Next thing that was actually introduced. So I mentioned earlier on that the GSM standard introduced like a combination of time domain and frequency domain multiple access techniques. And with UMTS, there is some introduced CDMA, or code division multiple access. So this is something that can be seen over here, right? So in one axis, we got the frequency channels, which are located along this way. The other line here, this is the time domain, TDMA frames. And if we go upwards, that means different codes. Okay, so basically using CDMA, it's by itself, it does not really bring much of the improvement because you're still using the same resources. But what it actually allows is adaptability in the sense of that with the GSM, the time frame, the time slots, and the frequency channel, that was kind of a fixed, right? Whereas here with UMTS, you can adjust your FDMA and TDMA and CD code in accordance to the access, right? So, for example, if you have user which is expected to download, let's say, like a big file from the internet, you can simply say, okay, I know this guy will need more communication throughput, so I will allocate, let's say, 2 time slots within the same frequency channel, or 4 codes or whatever. So basically, single user can use multiple orthogonal codes, as marked here by the red, or a single orthogonal code, depending on the needed amount of data that is being transmitted. So basically, the adaptivity and tailoring the throughput to individual need, that's adds significant flexibility. And here on the right, you can have like a simple example of how it can be divided. So we are assuming we have like 5 megahertz frequency channel over here. So that's quite typical for the systems. And if we have like a voice only, so by voice we mean just people calling each other, then we can serve within the same frequency channel up to 70 users, right? Then if we want to do some data transmission, so we can serve within the same resources, right? So with the same bandwidth, we can have 9 users requiring 64 kilobits per second, 5 users 144, and 2 users with 380 kilobits per second. Okay, and again, the adaptability is that you can mix and match within the same resources. So that's like a significant added value of the system. Right. So, any questions or any other idea? Well, concerns, or is everything clear so far? All right. So, right. Moving on, this is something I chosen two topics which I believe are also quite novel and interesting. From they're basically not exhaustive for all of the wireless communication, but they are, I believe, quite representative for the system. So over here we can see this is a classification of different wireless system, right? So basically, also including different standards. So WLAN, wireless local area networks, that's something which is very popular, and all of us actually, including myself, we use that on a daily basis. That's more known as a Wi-Fi, right? However, and this wireless local area networks, this is like a network, access network for internet, which typically comprises a building or section of the building or some relatively small area. Now, we can, of course, increase that to include larger size. And then we end up with wireless municipal area networks, so a bit larger area. There used to be a WiMAX standard, but it is sometimes still used. Well, it was supposed to be like a game changer. Apparently, it's not as widely adopted as it was initially expected. So this was basically, intended for cities, for local well, neighborhoods to provide, some public access network in public areas such as parks or things like that. Again, usually we have some, connectivity or public access points for internet. However, as far as I know, most of them will actually use the Wi-Fi standard or, IEEE 802.11 standard. Well, and then of course we can go to larger areas and larger area. What's interesting here is LP wide area network. Well, the reason why it is interesting is that this is a significant thing for something which is called Internet of Things. Okay, so basically the problem here is that you want to have like one access point which covers a very wide area, even up to several kilometers. But also the first two letters mean that especially the communication need to be in the low power mode. Okay, so this is intended for application of wireless sensors that are deployed in sometimes very remote areas. And well, the low power comes from the fact that you cannot go every month and replace the battery of your sensor now. So the energy needs to be used effectively, also for environmental concerns. Okay, so LP1, low power wide area networks. There have been some developments such as low power, well, IoT or LoRa networks. Again, with the idea of covering area up to several kilometers or even tens of kilometers, while being, very concerned about powers. And obviously, in that regard, we are not saying about the same connectivity as you have with your mobile phone. I mean, you probably charge your mobile phone like well, every 2 days, every 3 days. That's quite optimistic, even so. So in the, of course, the price to be paid here is that this is low amount of information. So it's really tailored towards, sensing applications. A classical way would be if you want to monitor rainfall, right? Or, well, you can deploy some moisture sensor. So you could basically get just one reading every minute or even every few minutes. And, then based on the fact that you have a very large area covered, you can build even real-time mapping of rainfall or, to prevent floodings, etc. So that's basically in the context of IoT. Okay, then when we go the other direction, so we have the wireless personal area networks and wireless body area networks. So with personal area, it basically means, well, anything that surrounds you, really. So over here we got the Bluetooth and Zigbee standards. So for example, I know if you got like remote speakers, right, connecting with your phone or with your computer, that would be exactly this type of communication. And kind of borderline possibly. So if you're using any smartwatches or things like that, then you're moving even closer to wireless body area networks. And this is actually the topic I would like to break down into some more details, simply because the radio propagation in the proximity of human body is well, very interesting topic. I mean, interesting in the sense that it is very different to other forms um, radio link. So typically we can say about three different types of body area networks. We have, well, on-body communication, in-body communication, and also off-body communication. So on-body communication, the most common case would be, your smartwatch communicating with a mobile phone that you got in your pocket. So in this case, the communications, is in the close proximity of the body, but still most of the communication is done in the free space, so through the air. In that context, you will have a very specific propagation channel. So you have a lot of multipath around human body, simply with the electromagnetic waves, reflecting from different components. However, still the electromagnetic or the radio signal, it would propagate through the free space or through air. Okay. And then what's also significant is that the channel can get quite dynamic, simply because of natural movement. If you walk, if you wave your hands, whatever, that would basically change your propagation channel here. Wait. And again, the classical problem here would be the smartwatch communicating with the mobile phone, mobile phone in your pocket. Now, contrary to this is in-body communication. So this is basically, well, nowadays the topic of medical devices, and especially any devices that are, really implanted into the body. So as we can see here, that's like sorry, here is the artificial kidney, which is communicating with some control unit outside. And well, we have more and more devices actually that that use this sort of communication. So there are, for example, some for gastroscopy. There's a research going on with, instead of doing gastroscopy, you can just swallow a pill with a camera. And then, that pill can transmit a signal out of the body, for doctors to monitor what's happening there. Well, the main challenge here is that humans are basically, pretty much bags of water, right? So 60% of our body is water, which is basically dielectric that, is lossy. So it attenuates the electromagnetic energy quite strongly. And that is a challenge, of course, because, if we, I keep repeating, right, that in the free space propagation, you have the, attenuation to the power 2, which is already quite bad, right? Now, in the context of human body, you would have actually attenuation that is much worse, much higher with distance. So that's kind of significant. Luckily, in terms of in-body communication, we are communicating over much smaller distances, right? So this is basically the reason why we can somehow made it. And typically how it works is just like you want the communication to be from the implanted device to the something which is mounted on the surface of the body, and that's like a one link. And then of course that device would do the demodulation, and if there is a need, it would use on-body communication further on using Bluetooth or some common protocol. So even basically getting the modulated signal out of the human body can be challenging because of the tissue is typically extremely lossy medium. Another two problems which are also very significant is the antenna size. Okay, so we touched that very briefly, but you can imagine that for medical devices, if you want to implant something into human, you prefer that to be as small as practicable, right? You don't want it to be big, which I hope is obvious. However, we already talked that typical antennas are resonating devices, which means the most simple classical antenna is like a half of a wavelength, right? So basically, that means that if you use very simple trivial antennas, well, you can reduce antenna by going higher with frequencies. So for instance, if you want to use 20 gigahertz, that's the millimeter wave range. So your antenna can be just a millimeter size. The problem is though that if you think about the penetration into the human body, you actually want to use lower frequencies. Okay, simply because the millimeter wave signal, it would be reflected basically from the skin. So 20 gigahertz has a very small chances of getting into the body. So for that, you want to use lower frequencies, which have much better penetration into the tissue. But then again, of course, for lower frequency, you need larger antenna. And of course, there are some ways of antenna miniaturization, but it's not given. So in general, this is a bit of a problem. So most in-body communication, they would indeed use the lower frequencies, so around 900 megahertz, 2.4 gigahertz, similar as Wi-Fi, and rely on some antenna miniaturization techniques. And lastly, the final problem is, of course, the power source. I mean, sure, if you've got an implanted device into human body, you cannot do the surgical operation every now and then just to replace the batteries. And of course, that's also problematic. So in the context of, what we said earlier on, that, well, we have a lossy medium, which means your signal is weak. And then if you want, of course, you can increase the transmitted power to improve your link budget. That's something we discussed in the past, right? But then, well, apart from other problems that may occur, we will discuss in a few slides. You simply deploy your battery quite soon enough, right? So how to power your transceiver in the context of medical devices, that's quite a challenging task. All right. And then the last type of the communication, out of body. So again, this is something that we have extracted some biomedical data into the node which is outside of the body, and we want to transmit this further on into the wider networks and Wi-Fi access point. Two things. So still in that context, the body will somehow affect the communication and our antenna. However, it's less significant than in the previous two cases. And basically, we can have off-body communication where we basically have one node located on the human communicating with something that is not in the human body, and we can have body-to-body communication. The difference is that in the case of the body-to-body communication, both sides of the link, so both transmitter and receiver may be affected by all the consequences of body area. Whereas in the case of off-body, it's a bit more easier case, simply because only one side is of the link is affected. All right. So I know. Do you have any questions towards this and yeah, for general the communication in proximity of human tissue? All right. I mean, in general, what I wanted to point out is that this is just scratching a surface, and merely to tell you that such a systems do exist. However, this is very very wide topic, and of course we don't have time to exploit that over here. Now, a little bit notion on the frequencies. So typically I mentioned that especially for in-body communication, there are like lower frequencies are preferred because of the increased penetration. And those are basically some of the frequencies which are basically dedicated to medical devices or body area networks. So right, as you can see, they can range from a few megahertz up to, well, in the case of ultra wideband, up to even 10 gigahertz. Usually, though, the frequencies around 900, 433 or 2.4, that's the most commonly used standards. Right. And here we also have some examples, interesting example of antennas for in this context. This is on-body antennas. So we can see here we get a connector, and one proposed antenna design is to use a zipper, which is basically a metallic structure embedded into that can be used as an antenna. So that's one option of antenna design suitable for body area applications. Here we got also some material-based antennas. So in this context here, this is like a very specific so-called monopole antenna. And this part is simply conducting embroidery, right? So this is all stitched together, whereas the general fabric is considered as a low permittivity dielectric, whereas this components here it's basically conductive. All right. Other examples. So this is an I think this is probably an RFID antenna, which we'll be talking in a moment, embedded in a lens. The device was made for monitoring, what was that? I believe it's blood sugar level in the eye, or sorry, pressure in the eye, and that can be also done. Now, in that case, there is probably no power source here. It's more on RFID, and we can also have some specific antennas. This would be the case of a wristband. So this cylinder here is basically like mimicking the effect of human hand, right? With antenna wrapped about it, simulating 2.4 gigahertz antenna that could be used for a smartwatch, for example. All right. This is some requirements for different types of medical applications. So obviously, different type of applications require different communication speed or different throughputs, as well as delays. So you can basically see that the speech, video streaming, and audio streaming, those are very heavy throughput, which intuitively again makes sense, right? Because especially video streaming is the quite large amounts of data, and here we can see the latency, which especially in the case of video streaming should be less than 100 microseconds. This is mainly because the fact that you want to have a smooth transmission. You don't want to have any delays here. So compared with those values, we can see that most of the medical application they require very low amounts of data being transmitted. With the EEG and electrocardiograms having relatively high amount, but still endoscopy. So endoscopy, this is the application I mentioned earlier on when we are actually trying to transmit some images from inside of our patients. So, but in general, especially in the terms of drug dosage or deep brain stimulation, again, the amounts of required data are quite small. And also, as you can see, we can afford quite a long delays, right? Simply because, it's usually not so much time critical application. However, what we need to, when we need to be like more critical is the low bit error rate. Okay, so basically the bit error rate for medical application is much more strict than for common application. So this basically means that only one bit over 10 to the power 10 might be flipped. As opposed for the streaming applications. And the reason, of course, behind that is that those are very often life critical applications. Okay, so basically, if you have an error in audio streaming or video streaming, I mean, sure, you can get you will get discomfort in watching the video or audio, but I dare say most of the people can live with bad quality videos. Whereas in this context, you really cannot afford a mistake, right? So basically, few bits flipped can cause serious damage to your patients, right? Because, for example, they would have a different amount of drug injected into their body. All right. Now, since we are mentioning biomedical applications, there is something which is I have to mention, is a specific absorption rate. Okay, so this is actually a generic metric which is most often referred to in the mobile phones, but it's of course general. So basically, the problem here is that as I mentioned earlier on, human body is basically 60% water, which is a lossy dielectric, and as such, it got a tendency to absorb electromagnetic radiation and dissipate it, as a heat. So, in the worst case, if you're standing, next to a radio transmitter which has like a few kilowatts of energy, well, you can get burned from this. Again, we're talking here about really high power applications, right? So anyway, in order to make sure that this is not the case or this is not happening, there is the metric of specific absorption rate. So this is basically a metric which tells you how many watts of radio energy, actually it can be any form of energy. So similar metric would be used, for instance, for ultrasound, but here we're discussing that mainly in the context of radio signals, right? So Specific absorption rate, it tells you how many watts of energy are absorbed by 1 kilogram of tissue. Okay, and when we speak about tissue, we most commonly think about human body, human tissue, but obviously that can be any live being, right? So you will have a similar metric for animal specific application. Okay. So furthermore, any radio device available on the market, and that includes also microwaves, even though the microwaves are enclosed, right? So typically you don't have any radiation getting out of the microwave, but still they're using radio signals, and medical devices. It needs to be certified, to demonstrate that the specific absorption rate values are within safety limits, right? So this is like basically a very rigorous safeguard, in order not to prevent any damage to us, right? And any health issue in the general public. Okay. So typically, according to European law or European Commission legislation, in the context of mobile phones, there is a requirement that the SAR cannot exceed more than 2 watts per kilogram. Okay, so basically in every kilogram of human body, you cannot lose more than 2 watts of energy. And of course, 1 kilogram, that's a very, very rough metrics. So typically, not typically, according to the requirements, this has to be averaged, of course, over 10 grams of tissue. Okay, so basically 10 grams of tissue, that's something that can be measured and done in quite a detailed manner. This 2 watts per kilogram, this is a standard for head and trunk of the body. If you think about so-called extremities, so legs and arms, the standard here is 4 watts, so double that. Simply because typically in arms and legs they're just muscles and bones, and there are basically no vital organs. Whereas for head and by trunk we mean the main body of human. This was lowered to 2 watts, and also this phrase refers to the general public. So what we mean by that, it's simply the ordinary users, customers that you're. So basically, this means ordinary people. However, there is also a little bit relaxed limit on people working, on basically technicians or people directly working with radio equipment. So, for instance, if you'd be working, as a base station service, high climbing on top of the base station mast, then you can be hypothetically exposed to slightly higher specific absorption rate, right? But this is because in such a circumstances, you would of course undergo a special training on, or on how to deal with such a situations and avoid the exposure. Whereas of course, you cannot expect paying customers to follow the same guidelines as trained professionals. All right. Now, what's important that this has to be calculated with respect to the maximum power allowed to a standard. So I believe in a way, intuitively, it should make sense. Simply because with the health and safety, you typically account for the worst case scenario, right? So by maximum allowed power, it means really the maximum power that your device, your mobile phone, can generate. A note here is that usually most of the mobile phone standards, they use smart adaptive power levels. So typically, especially if you're actually in a proximity to the base station, your mobile phone will reduce the amount of the power that it's using, simply because it basically goes back to the link budget equation that we discussed in the past. So if you're in the close proximity to the base station, you need like a lower power to transmit the same messages. So apparently, in some context, closer to the base station, you will counterintuitively experience lower exposure, simply because your phone can use lower power to get the same performance of the link. So what I'm actually trying to say here is that your mobile phone typically very rarely operates with the maximum allowed power. That will be basically the case for if you have a macro cells and you're like very far away from the base station, then because of the distance, I mean, we all did the link budget calculation, right? So because of the distance, you need to increase the transmitted power to satisfy the link budget equation, right? So that's typically the most critical part. However, as I said, most of the time, the phone will operate with much lower power than those used for calculating specific absorption rate. And finally, for mobile phones, typical values include two locations for measurement. So one would be placing phone close to your head, which is in a pretty much normal way of how you talk over the phone. And then also in the proximity of the body, typically it's around hip level. So this is more, for the case where you're not talking, but either you have your phone in the pocket or, you're using data for your phone. And again, for both these cases, there are those strict specific absorption rate in place. And again, it's not only for phones. So over here, it's just like an example. This is actually not a phone antenna, but it's just taken from a scientific paper about the medical devices for some brain monitoring medical device. And over here, where we see the specific absorption rate, how it so obviously the area closest to the antenna is the most highly impacted. Right. However, and this is basically done with a simulation. So we can, model and simulate those processes quite accurately. Typically, a simulation takes a while because you need to have some heat calculation. But okay, you typically do it, of course, once or twice per device. That's quite well understood, basically thermal effects on human body. And as you can see here in this paper, the proposed device, so over here you see the yellow area, which might sound kind of dangerous, but if you look into the scale, it's actually 0.016 watts per kilogram, right? So it's like not even close to the legal limit, which again, of course, this limit was proposed by medical doctors after research, and that's kind of something that is deemed safe. So you can see this particular medical device is not even close. It's basically 2 orders of magnitude below the required level. Right. And for mobile phones, typical values actually are even below 1 watt of kilogram. That's basically what we can achieve with testing and measurements. If you're really interested in the topic, there is a website called SARTIC, and well, among more detailed information, or how SAR measurements are performed. If you're interested, you can actually find the manufacturer's data, and you can actually look into specific absorption rate in accordance with the EU European Commission standards for different phone manufacturers. Typically, as said, you will find two SAR values. One measures with respect to the head, so when you're just holding the phone next to your head, and the second one with proximity to the body. So if you're interested, I encourage you to look into that website and see if there is data about the phone that you're using. Okay, so this is the standard. Now, a little bit of information how it is actually performed, right? Because as I mentioned, every product, every phone on the market that is operating in the proximity of human need to be certified. And basically, this image basically shows how this is done. So what we got here, here we got like a phantom. So this is in that case, it's a testing of mobile phones. So we have a phantom in the shape of a human head, and it is basically filled with a liquid, which aims to mimic, human tissue. So it's not exactly, it's basically an average proper electromagnetic properties of human body, or in the kind of head of the human body. So we're talking here about, same permittivity, same permeability, and same conductivity as on average human tissue would have or has. In practical terms, of course, a skull or a bone would have different permittivity than a muscle, than the human brain, and so on and so forth. However, this is typically, averaged in a homogeneous liquid. Now, here we, of course, have the device under test, holded by this, by the structure pressed against the phantom in normal, operating conditions. And of course, it is fed, or it is operating in the very same way as it would in a daily operation, with same power level, same modulation, and so on and so forth. And here we simply have a temperature probe, right? So this allows us basically to put the probe into the phantom, into the skull, and simply measure over a certain time what is the increase of temperature at a certain location, right? And this data can be later on recalculated to the specific absorption rate. And then, of course, we have a mechanical arm which allows us to sample different location, right? Because as I mentioned earlier on, the values should be average over 10 grams of tissue. So that more or less corresponds to few centimeters given density of human body, right? But of course, it's not enough that you just sample one point into the body and say, okay, hey, I'm good here. I mean, all right. As we saw on the previous slide, different parts may be differently affected. So typically we have this mechanical arm to, sample all volume of the head, just to make sure, again, there is not a single point which would exclude the SAR standard, simply because that would prevent the product on being deployed on the market. Right. And here's basically another, it's a DAISY system. You can see pretty much the components are roughly the same, just in this context, we have the liquid in an open bath tube. And here we're just interested in a device that is, it's not a head phantom, but it's, I think it's a full body model here with the radio device being mounted underneath, right? So it's a bit different use case here. Right. So are there any questions relating to SAR or to this part of of the lecture? Right. I mean, one reasons why we actually decided to include this topic into the model is that you're probably aware that there has been recently quite a lot of misinformation and different data about the 5G, even like, well, I shouldn't comment really on that, right? So yeah, so basically the SAR, the specific absorption rate, it's actually not a new thing. It's been there for like decades. Again, even for decades, for sure, for years actually. I should be careful here, but definitely not a new thing. And I said there's like a strong certification required to make sure that radio devices are basically not causing any damage to humans, right? At least with the effects, the physical effects that we are aware of. All right. So with that, I would like briefly to mention our last topic, and that's radio frequency identification. So again, this is quite commonly used thing even with the credit card. With the pandemic, contactless payments are being very, very popular. So that's a bit of a glimpse into the technology and how it operates. So the idea here is it can operate through different bandwidths or different frequencies. We'll talk about them in a moment. But basically, the RFID consists of two components. So we got an RFID reader, which is typically like a small tag that is typically low cost, very often passive, although not necessarily so. So in the case of RFID reader, that can be like a fob from your keys. That can be your credit card when you do contactless payments. Your student ID card, they also got embedded, RFID tags. And the tag just contains some like a chip with information with. Sorry, I explained that first in the reverse direction. So here basically I start with the tag, which contains the data used for identification, hence RFID. And then the reader, this is basically the device that allows reading of the tag. So the reader, that would be mobile payment terminals, that would be a lock to open the door, that different ways. Okay. So then there's a so-called interrogation zone, which basically means this is the area where you can have a communication with between tag and the reader, right? So this is typically up to a few meters. The range is very, very small, and this is because, of course, the tag it's passive. So it is, or in most cases, it is passive, right? So it accepts basically the power from the reader, which is used for powering and transmitting back information. And of course, because of the link budget requirements, you have kind of two links that are performed in series. So first link is the amount of energy from reader into the tag. And as we know, that's the case with power 2 of the distance. But all of the accepted power will be used to power the second link, which again, the case with the power 2 of a distance. And because of those two links are like, you can see them as in series. So overall, the power of the systems will deteriorate with the power 4. Okay, simply because you first need to deliver the energy wirelessly and then transmit it back. So that's the typically very strict limitation on why typically RFID systems have a low interrogation zone range up to a few meters. In general, there's some variation. So this can depend on the technology you use. So it will be lower for the lower frequencies, around 100 kilohertz. If you go higher with the ultra high frequency range, you can get, a little bit more range. You can play a little bit, of course, with configuration, but typically a few meters is the maximum you can get. However, for many actually applications, the classical would be here contactless payments. You actually do not want to have too large interrogation zone, right? Simply because in the case of credit card payment, you really want somebody to put it within up to 1 centimeter from the reader, to make sure the transaction is made intentionally. Right. So an RFID tag, how a typical tag looks like, and those are all examples operating at different frequency. It basically consists with 3 elements. Well, so 2 radio components. So it's basically just a chip, which contains some information encoded into that chip. Usually, it's just a number, which is used for later on references. And then there is an antenna or a coil, depending on the frequency you're using, which does in the transmission. So firstly, it powers up accepts the radio energy to power up the chip. And then, once it's powered, it transmits back the information. Okay. There's typically a sort of a substrate, but that's mainly for mechanical support. And optionally, there is they can be either a battery or energy harvesting device. Okay. So this is the distinction between active and passive tags. And of course, if you include battery or any energy source within the tag, that can actually substantially increase the reading range of your device. Okay, so that's something that should be taken into account. All right. Now, this is an overview of different frequencies. So basically, I'm gonna maybe to go through that rather quickly. So, well, basically the lower, yes.
So I assume that a simple RF tag can just have like a number that it sends to the reader, but like a credit card, let's say, it needs like a public and private key, and because it can just broadcast the key to whatever, right?
Yes, obviously. I mean, if you need, yes, of course, you're right. I mean, yeah, of course. For some application, of course, you want to have embedded security. That's correct. I was more focusing, on a more simple application. So I mean, still that key would be embedded. The public key would be embedded. Into the chip. So with that regard, of course, the public key can be basically seen as the information. What I was more trying to say here is that the RFID chip, it has a very limited processing power, right? So it's more used to store the energy, maybe some very simplistic operation, right? But you don't really perform any computing within the chip that is in the tag. That was the main message here. So yeah. All right. Okay. Yeah, thanks for clarifying that. Okay, so well, the low frequency RFID in the 100 kilohertz. So again, the same the same principle as we talked earlier on with electromagnetic propagation is that the lower frequency, they typically allow larger penetration into water or into any dielectric tissue. So that's typically might be advantages for tagging, like animal tagging applications, animal marking, but also in terms of the wavelength, they typically operate in the near field. Yeah, simply that antenna miniaturization or the coil is very small here. Then we have, we go upwards with frequency. And so, sorry, what you mentioned on the 13 megahertz tag, that's the one, as you see here, used for contactless payments. And well, basically the rule, how it works at this frequency is you can see low frequency and high frequency systems, so up to this 14 megahertz. Simply you can see the antenna more acting as a coil than an antenna. So what is happening here is that you have the power source with one coil, and the another coil will be embedded and connected to the chip in the RFID tag. And then if you put them together, well, you effectively have like a transformer, right? So basically the one coil will induce some current, some electromagnetic energy in the second coil, and this is the way how you can communicate with the tag, right? So it can be really seen as at lower frequencies as a very simple transformer that is being created when you get the tag close enough to the reader. Okay. Now the question here is how to transmit information here, right? Okay, let's. Okay, so sorry. One more thing I should say here. We go back to the modulation aspects later on. So what's also important that's from the basic electromagnetic course, really, right? That because this acts as a coil and it requires induction of current into the secondary coil. And of course, the amount of energy induced is proportional to the effective area of the coil within changing electromagnetic field, right? So typically when we have the two coils parallel, there's really no problem, right? Because the coils are facing each other. There's a large area within which they interact with each other. So we get like the maximum of energy induced into our chip, right? The problem, of course, comes when, and that's something that you cannot guarantee upfront, is when your RFID tag is placed orthogonally to the reader. And the problem here, of course, is that then the area of the effective area of the coil over which it can interact with the changing electromagnetic field or magnetic field actually is very limited. So the power induced is also small. Now, this wouldn't be a really much problem for, let's say, door opening systems, right, or card reading, because then you can the user puts the tag in a specific position. However, with RFID tags are very often used for safety system. So, for example, I don't know if you do shopping in Decathlon. I'm not quite sure if it's I think it's most of the shops they got actually RFID tag shopping. So what do you mean by that? Is that you do your shopping over the phone, and every single item got like an RFID tag sewed into the clothing. So when you go to the self-serving counter, you don't even need to scan the barcode. You just put the device into the special basket, and the shopping system reads the tag, identifies the clothes, and charges you appropriate price. So that's quite efficient way of shopping, right? Of doing shopping. And as I mentioned for this application, you will have RFID tags in different orientations. So you can really guarantee they will be always parallel to the coil. So in practical terms, what is used, the shopping system, they would use simply multiple coils, which preferably are located orthogonally to each other, right? So that there is, if a tag is orthogonal with respect to one coil, it will still interact with the remaining. So that's like a, safeguard against thief, or against people moving, taking basically items out of the shop without paying. All right, and if by any chance, well, I don't want to make, of course, advertisements here, but if you do your shopping by any chance in Decathlon in Wrocław, next time you can actually look for the RFID tag that is sewed to predominantly to clothes that you buy, and you can actually see the material with tag and antenna embedded. So that's a bit of a curiosity how it works. All right, now I asked earlier on the question about how the modulation is done, and of course at lower frequency we mentioned that there's the coil approach. However, if you move upwards, then the reader and the tag, they're actually more modeled by antenna, not a coil. I mean, the exact difference between when it's still a coil and when it starts being antenna is a bit liquid. However, okay, so in this case we have reader with the antenna transmitting some EIRP, effective isotropic radiated power. So that's something that we discussed, and basically we got a reader, and it is typically constructed like this. So we have here the antenna of the tag. We have some matching circuit here with the load, and the load is set A here. That's the antenna impedance, and ZC, that's the characteristic impedance of the chip. There's typically some matching circuit which is designed to accept the maximum possible amount of energy for powering the chip. And here actually you can see the chip itself, right? So basically, and how does it work? Well, earlier on in lecture 9 we talked about the reflection coefficient of a system, and this is exactly something which is used here. That's just one of application really. This is basically something that is used in RFID systems. So basically what's happening here? Well, we got antenna which accepts some power, puts it into the circuit, and we already know that when there's like a mismatch between the two impedances, it will cause a reflection, a certain reflection coefficient, right? So basically, if the two impedances are the same, all of the power is accepted. If there is an impedance mismatch, part of the energy will be reflected. Okay, so here we get some impedance ZA and set ZT, and basically, if they are the same, well, there will be no reflection. So all the power will be dissipated in our resistance ZT here, right? However, we get also the output to the chip here, and what the chip can do, it can, for example, make a short circuit to the ground by effectively bypassing this impedance ZT. So that will like replace this specific impedance with a short circuit, right? And we already know what will happen. We done this calculation before. So obviously, if there is a short circuit here, then then we'll have a total reflection. So the signal will get reflected from this point, go back into the antenna, and then through the antenna, it will be actually transmitted back into the reader. So those are like basically two states. So it's a very simple modulation in this case, but we get 0, which is, let's say, no reflection, and 1 means total reflection, right? And then, of course, once the chip is powered, it can usually execute the series of 1s and 0 in sequence. So effectively, by playing with by changing the impedance, we can have change the reflection coefficients, which effectively, from the reader point of view, would be seen as a very simple amplitude modulation. Okay, and that's basically how passive RFID tags would work. Okay, so is there questions to this? Okay, so I hope that's clear. Now, one thing maybe that should be pointed out here is that as we know, this technique, so controlling the reflection, it's a very smart but also very primitive, simple way of communication. So as you know, this would of course impact the amount of data that we can transmit. But as I mentioned, usually we don't need a lot of information. So typically, and as again, there are like some exceptions, like with the public key in the case of the credit card. But usually, the RFID contains just the identification number, and so for instance, within the reader, those identification number would be put against the database, which is in the cloud or in the network, and that's basically where the reminder of the processing will work, right? So for instance, if you top up your let's say your ticket for the public transport with certain amount of money, those money will be not held really on your passive tag. So your passive tag would have only transmit this number, and the amount is actually recorded in an external database. Okay, so that's the message here. And here you can see that the sequencing, so how the modulation is done. And basically that's it for the lecture. So well, it seems we are almost perfectly on time. So again, if you want to ask anything, feel free to do so. There'll be also a consultation time. We're starting pretty much practically right now, or in a few minutes. Yeah, so with that, I would like to thank you for your attendance. Wish you, as usual, a nice weekend. I hope you already slowly start preparing for the exam, because it's narrowing. And yeah, in 2 weeks we'll try to do like an overview of all the things that we discussed from lecture 1 up to now. Okay, so if there are no more questions, again, thank you very much for attending, and see you in 2 weeks' time.
I want to say something.
Yes.
So it's not a question, it's a remark which I wrote on the chat some time ago about low power wireless systems you were talking about. From what I know, substandards for LTE for low power devices required for device to be certified. It's required that it can run for 10 years without change of battery.
Yes, exactly. That's something I wanted to highlight here. So yes, so that's basically the design principle, right? And that 10 years of without battery change, this is exactly the thing which would dictate the way of operation, right? Because of course, if you would have the very same communication as with mobile phone, there's no chance that the battery will last 10 years, right? So that's why typically low power one would, as I mentioned, first, very often they would actually have a specific modulation type, as for example, in the case of LoRa, the modulation is very specific, in order to minimize the amount of energy required to transmit the signal. And secondly, of course, it would also require reduction of the amounts of data being transmitted. So again, usually we're thinking about smaller amounts of data, and transmitted in relatively large time intervals. And that's how this 10 years is achieved with design. Okay, but yeah, that's correct. So.
Okay, so design.
Thank you.